Everybody. Today we are honored to have Professor Jinho Kim at this seminar series. So I will introduce him shortly. Professor Jinho Kim is a probably productive researcher in diverse areas such as demography, social epidemiology, children and youth, aging, and social networks. His articles have appeared in reputable journals, Social Science and Medicine, Journals of Gerontology, Journal of Aging and Health, Social Science Research, Youth and Society, and more. And in the past 6 years, he published more than 30 journal articles. After his doctoral program at the University of Wisconsin Madison, he worked as an assistant professor at the Chinese University of Hong Kong. Now he's a faculty member of the College of Health Science at Korea University. Today, he will give us a talk entitled A Big Male Fish in a Small Pond, the Gendered Effect of Ability Rank on Adolescent STEM Aspirations under Gender Math Stereotypes. Thanks for the talk and welcome to CFPR Seminar Series, Professor Kim, and we are all ready to listen to you.
Hello, good afternoon. So let me first share my screen with you. So do you guys see the screen well? Okay, awesome. All right, so it's my honor actually and privilege to speak to you about my research today. And this is actually a joint work with, excuse me, Ron Liu, the assistant professor of educational policy at University of Wisconsin Madison. And also Xiang Zhao, a fresh PhD in CHK sociology and an incoming assistant professor at Chinese Academy of Social Sciences. So let me get started. So looking at current global trends in educational attainment, as many girls as boys are completing high school education, and there are more women who are receiving college education worldwide than men. And about half the workforce is women in the world. Having said that, what has been pretty obvious these days was that women still remain a minority, and especially in science, technology, engineering, and math, STEM in short fields across the world. So then what are the consequences of this gender differences in or underrepresentation of women in STEM fields? This persistent gender gap has contributed to occupational sex segregation, and also it aggravated gender gap in earnings, right? Because STEM jobs are often better paid. Moreover, it can also lead to the underuse of valuable intellectual resources, given a fast-growing demand of specialized STEM workers. So because of this globalized and ongoing trends, and at the same time, the negative impact on gender equality and national economy, so this underrepresentation of women in STEM fields has kind of initiated an intense academic and public debates about its causes. So given gender similarities in educational achievement and attainment, and then what then drives such a large gender gap in STEM fields? This is kind of motivation of this study. And STEM pipeline analogy helps explain lower rates of STEM graduates and workers. So the idea is pretty simple but very powerful. So the idea here is to see where leaking takes place throughout the whole pipelines of pursuing STEM careers. So there are two main principles actually in this analogy. So one of which is that it's important to remain in the pipe as long as you can, right? So once you leave the pipeline, and it's almost impossible to return. The second, it is not a once for all leak in the pipeline. So leaking happens in different stages of life, and it also happens in different stages of a career trajectories. So this leaky pipeline concept kind of seems to be useful to systematically understand how and why women drop out of STEM fields at all stages of trajectories. So we can broadly distinguish the trajectory into three different parts, right? As you can see in the slide, secondary school and college, university, and industry. I'm going to actually giving you a brief sense of what can happen in each one of this, stage. So for example, during secondary school, some female students have higher STEM aspirations than others for, several reasons, right? Then not all, but some of those interested in, STEM careers may ended up with STEM majors in college. And during college, some of those majoring in STEM fields may drop out and change their majors, right? And after graduation, probably, many of, but not all of those with the STEM degrees get STEM careers at the end. So during the career stage at the same, also, for various reasons, some women may decide to leave their STEM jobs. So among different stages where the leakage might take place, we just wanted to look at how early school experiences contributed to gender development of STEM aspirations. So why schools are an ideal and important context to study gender differences in STEM aspirations. There are two major reasons. So number one, except home, school is the most important context, maybe for socialization and social comparison among adolescents. So it's kind of a microcosm where young students interact with different social actors, including peers, teachers, and other adults. Second, as I explained in the leaky pipeline metaphor, it is crucial for beginning with a higher base level to retain more female STEM workers, right, at the end of the trajectories. So larger influx is very important. So schools are places where we can secure a larger base, right? So for these two reasons, I think schools are the most important context that we want to look at if we want to know what is going on, with respect to the underrepresentation of women in STEM fields in general. A natural follow-up question then might be, why are women less likely to aspire to enter and more likely to leave STEM courses, STEM majors, and STEM careers? So studies consistently found a female disadvantage in STEM aspirations at early educational stages across the world. So there is of course, a whole tangle of reasons why the gender gap in STEM exists, but we just wanted to focus on two big broad, broad mechanisms here. So we can frame this in nature versus nurture type debate. So nature explanation. So potential gender differences in cognitive ability, especially math skills and math ability, used to be seen as a plausible explanation to early gender differences in STEM aspirations, because as you know, math ability is a precondition to succeed in STEM fields, right? However, while earlier studies observed patterns of gender differences in math ability and math performance, but more recent evidence has increasingly shown gender similarities rather than differences in math ability. So girls have kind of reached parity with boys in overall math performance at minimum, And girls even outperform boys in some math-related abilities, such as like object identity memory or like object location memory, according to the studies, recent studies. Actually, in our own data set, we also found gender similarity in cognitive ability with a particular focus on math skills. So this figure presents the distribution of cognitive ability score by gender. So as you can see, on average, girls' cognitive ability is slightly higher than boys, but which is not statistically significant. And the variance, there are some differences, gender differences and variance in the distribution. So the variance of a boy's ability is slightly larger than that of girls' ability. But basically, the takeaway message from this simple picture is that at least in our data set, we can actually reach the same conclusion that there is gender similarity in cognitive ability. So if we rule out nature explanation, we can then redirect our focus on a competing nurture explanation. So studies have shown that even with the same level of math performance and ability, somehow girls still have a lower self-assessment of their math and science abilities. So studies also documented the effects of certain gender stereotypes. For example, boys are naturally better than girls at math and science. So such stereotype leads to gaps in performance and the sorting of boys and girls into different fields of education and different fields of occupation as well. So in the school setting, female students exposed to discrimination and stereotype about female math ability might generate lower confidence and lower interest in STEM subjects among female students, and consequently lower levels of STEM career aspirations among them. There has been a growing social psychological literature that proposes to incorporate the processes of a social comparison and to examine the role of a relative ability or a student's ability rank in their peer group. So a seminal work, so as you might, many of you might know, a seminal work by Marsh examines the big fish little pond effect, showing that equally able students earn higher grades and develop higher academic self-concept and self-confidence especially in schools with a lower average ability. So he argues that the students are surrounded by lower performing peers may develop stronger beliefs in their own academic ability, thereby investing more in their human capital and forming higher aspirations. So in support of this idea, many later studies shown in the slide have provided empirical evidence to this big fish little pond effect theory, showing that given the same level of the absolute ability rank within the peer group plays an important role in producing disparities and different outcomes, as shown in this slide, all these outcomes. So despite the large literature on relative ability and various educational and life outcomes, very little is known about whether and how relative ability affects STEM career aspirations and whether there are any gender differences. So some previous research has documented evidence of gender differences in self-evaluation through social comparison, which means the impact of a social context is not homogeneous for men and women, and it has a differential gender differential impacts. So, for example, male students tend to attach greater importance to social comparison for the development of self-esteem than girls do. And boys are more likely than girls to rely on within classroom comparison to develop self-concept, and they tend to believe they are better than most of their classrooms. So although this is thus, reasonable to speculate that boys may benefit more than girls from social comparison in the school context, the actual process of social comparison, especially the role of relative ability in potentially producing gender differences in STEM career aspiration, is still largely underexplored and overlooked. So summing up, this is the first limitation in previous literature. So when it comes to gender disparities in STEM aspirations, social comparison process, especially the role of ability rank, is still underexplored. So to address this first limitation, in this study, we asked the following research questions. So is there an effect of ability rank on adolescent STEM career aspirations after controlling for students' own absolute ability? And if yes, and does ability rank affect male and female students' STEM aspiration differently, thus producing gender disparities? So to further extend the research questions that I just posed, to understand the role of a social context, the role of the social context in generating gender disparities in STEM career aspirations, we can bring in contextual gender math stereotypes in this picture. So more specifically, we can consider the possibility that potentially gendered effects of relative ability on STEM career aspirations might be conditional on a particular social and cultural atmosphere, especially in terms of the gender math stereotype. So gender culture beliefs or gender stereotypes have been examined as important factors leading to gender differences in STEM aspirations. For example, there have been a widespread gender math and gender science stereotypes, right? Especially in East Asian context. So math and science are often seen as masculine, and because they require logical and analytical thinking, and also it is widely believed that men have a higher competency than women in these fields. In that regard, gender stereotypes are known to disadvantage women's performance and educational outcomes. However, when it comes to the social comparison process, again, we know little about the potential interaction between student ability rank and the stereotypical environment in producing gender disparities in STEM career aspirations. So it is unclear. So this is second gender gap. So it's unclear whether and how social comparison process might interact with gender stereotypical contextual environment in producing gender disparities in STEM career aspirations. And to what extent this process varies as student exposure to stereotypical environment changes. So the third research question here in this study is to examine whether potentially gender effects of relative ability on STEM aspiration depend on one's exposure to gender math stereotypes within the peer group. So graphically, we first examine the link between relative ability and the development of STEM career aspirations, net of absolute ability. And then we examine whether the effect of relative ability is greater for boys than girls. So we're looking at the possible moderating effects of gender in this relationship. And finally, we further examine whether this potential gender math, we're looking at whether the gender math stereotype, among peers amplify the potentially gender effect of ability to rank on STEM career aspirations. So in this study, we use China Education Panel Surveys, SEPs in short. So this is a school-based and nationally representative survey of 7th and 9th grades students in China. So the survey team randomly chose like 112 schools and then randomly chose two classes in both the 7th and 9th grades in each school. And all the students in the selected classes were surveyed. So in this study, we use a quasi-experimental research design to identify, hopefully identify causal effects of relative ability. So to address endogenous school choice and non-random student sorting that are often, difficult to observe and measure or account for, we exploit idiosyncratic variations or exogenous variations in classmate composition within the same school, of course, under the big assumption that students were randomly assigned to different classes. So we'll talk about this assumption in greater detail shortly. So we just want to move on just for now. So then now let me briefly explain where the variations of our analysis, empirical analysis, can actually come from. So the variation can be driven by differences in mean ability across different classes. So in this figure, each classroom has a different level of, different levels of mean ability. So as red dots indicated. And because of class level differences in mean ability, a student with ability at X would have a different rank by chance, right? Because of a random assignment. So for example, in class A, she is ranked in 5th, the highest quintile right here. But if she was assigned to a class B instead of A by random chance, by random assignment rule, she could have been ranked in the 3rd quintile, so middle quintile, right? So this is a possibility, more plausible scenario than the next one that I'm going to explain in this slide. So this is another possibility, again, though less realistic, that the variation in classmate composition can actually be driven by class level differences in the variance of ability distribution rather than the mean of the ability distribution. So for example, in this figure, all 3 classrooms have the same mean ability, but a different variance, right? So in this case, a student with, again, ability at X is ranked in 4th quintile in class A, but could have been ranked 5th in class B, right? So we use the variation, which comes from the fluctuations in the ability distribution across different classes, potentially created by random assignment of students within the same school. So this slide shows to what extent relative ability varies by absolute ability. So each box plot here shows the variation of respondents' percentile rank for a given deciles in the global ability distribution on x-axis, right? So as you can see, the measures of absolute absolute and relative ability are not perfectly correlated, but there are quite large differences. So for example, those in the 6th decile of global ability distribution can end up being almost anywhere, right, between 0 and 100 percentiles in the local distribution, which is like a relative distribution to a different peers and classmates in the same school. So we could say, like, you know, from the picture, there could be a quite large within school variations that we can take advantage of. So now, the big question here, the validity of this experimental design strictly depends on the random assignment of students to classes within school, right? So we take three approaches to leverage plausibly exogenous peer composition or classmate composition. So first, a unique feature of SEPs is that it contains the information, self-reported information on class assignment rules self-reported by both school administrators and homeroom teachers. So, so that is why we restricted, first of all, the sample to schools that randomly or averagely assigned newly enrolled 7th grade students to classes, and the schools that reported that they did not reassign 8th or 9th graders, so continuing students, to classes in terms of their previous academic performance. So, which means like there is no tracking. So basically this decision, again, is based on our trust on school administrators and teachers' self-reports, right? But again, the information, of course, could have been possibly incorrect. So to deal with this deal with this possibility, we conducted a simple but very intuitive empirical test that mimics analysis often conducted in randomized controlled trials. So which is called like a balancing test. So we examine here, we examined whether like students select into a class with a certain ability distribution. So mostly through school choice, right? So I'll actually give you more details about this procedure and what we did in balancing tests in later slides. So just keep it here. And the third approach is to conduct a series of empirical tests to more directly examine how plausible classmate composition we observe in the data is if students were really randomly assigned. So we're looking, are we actually having sufficient evidence of random assignment by looking at the data? This is the idea. So because of time constraint, I don't really think I can explain and show what I did in what we did in this study in this very talk. But in brief, we obtained sufficient evidence on random assignment of students to classes in our selective sample. Basically, if you're interested, you can refer to my own recent paper published at American Educational Research Journal. So you can easily find that out if you know my website, and you can, if you are interested, I can actually send it off. But anyway, so we actually took the very similar approach, and we used like a simulation-based test, and also we did some statistical tests whether the data really tells that the students were randomly assigned as the teachers and administrators reported. Okay, so for measurement, for relative ability, we used classmates as a reference group, and we computed percentile rank of cognitive ability, which ranges from 0 to 1. So actually the rank is the most basic, yet most salient form of a relative status, as far as we know, right? The SEPs conducted a standardized cognitive ability test, which aims to measure students' basic logical thinking and problem-solving ability. So most of the questions actually were about graphic and spatial ability and math and logical ability. So we believe this cognitive ability can be understood as a particular form of a test focusing on math-related dimensions of ability. Dependent variable is STEM career aspirations. So students were asked what they want to be, what they want to do in the future. So the answer quoted was 1 if students chose scientists or engineers, and 0 otherwise. And moderating variable of exposure to gender math stereotype was operationalized by the proportion of classmates, excluding the focal students who agreed that boys are better at math than girls. So these are the covariates we controlled in the empirical specification. So mainly sociodemographics and parental characteristics. But this is our specification. So dependent variable again is the outcome for student I in class C and cohort G or grade G and school S. So this is relative ability, relative measure of ability. And so here the beta is the coefficient of our own interest. So to make sure that the beta exclusively captures the impact of a relative ability, we control for absolute ability. So in the and we include actually a quartic in own ability as controls. So actually the justification for controlling for absolute ability is to compare 2 different students with the same level of absolute ability in the same grade, but having a different ability rank, as I described in the a couple of slides earlier with the kind of a graph there, because they are exogenously situated in different classes, right? So again, so the reason why we control for absolute ability and then like looking at the beta here is because we wanted to compare 2 different students in the same grade and same school, but differ in their ability rank because they were quasi-exogenously situated in different classes because of random assignment practice, right, in their school. So we control for, again, a quartic polynomial in absolute ability to more flexibly allow for possible nonlinearities in the relationship between absolute ability and STEM aspiration. But actually results remain similar when we control for absolute ability in different functional forms. So like a linearity, and we added quadratic and cubic polynomials of the absolute ability. And here S is a school by grade fixed effects rather than school fixed effects, because we more conservatively control for school by grade fixed effects to further account for potential unobserved school cohort level heterogeneity. Finally, the robust standardizers are clustered at school level. So before presenting main results, I show the results of the balancing test here. So the idea, again, I'm elaborating the idea of the balancing test here. So because of a school selection, school choices of parents, we expect that class mean ability are correlated with many student characteristics, right? Especially family level socioeconomic background. So we test this by running regression of class mean ability on several important student characteristics and parental characteristics as well. However, if students were randomly assigned to classes within the same school, controlling for school fixed effects or school by grade fixed effects would remove all these correlations. This is the idea. So we interpret the disappearance of the association and correlations as evidence that conditional on attending a given school, class-to-class variation in peer composition, and in this case, the class-to-class variation in peer ability distribution is plausibly exogenous, and so is students' ranking. So this figure presents results for regression without fixed effects. So each dot here is the coefficient from a separate regression, and I label it with the name of each variable, and the spikes presents 95% confidence intervals. So as expected, this shows the class mean ability is significantly associated with various individual characteristics, right? So female students and Han Chinese students are more likely to attend higher ability classroom. In contrast here, older ages and older students and students with rural hukou are more likely to attend lower ability classroom. More importantly, looking at this bottom of the graph, and a variety of family characteristics is highly correlated with pure ability composition. So students with a higher SES families increase the likelihood of attending higher ability classroom, of course. Moreover, students with living both parents and students with no siblings, so one only child, predicts students' selection into higher ability classroom or higher ability schools. But when we control for school by grade fixed effects, all these statistically significant associations disappear, right? And this indicates that there is a systematic school selection. To your left-hand side, graph shows there is a systematic school selection in real world, but within given school, class-to-class variation in ability distribution, in this case, the mean ability is exogenous or quasi-random because of this random assignment practice in each school. Now let's take a look at the main results. So the slide presents the estimates of the relationship between ability rank here, relative ability, and STEM career aspirations. So in the first column, bivariate results show that ability rank is positively associated with STEM career aspirations. So we did not control for absolute ability here in this first column. And in the next column, we added all the set of control variables, including quartics in absolute ability. And we found that the effects of relative ability on STEM career aspirations are robust to controlling for all these covariates. So our results support the first hypothesis. And to examine gender differences in the relative ability effects, and we added interaction term of ability rank and female indicator. So as you can see here, negative and statistically significant interaction term suggests that ability rank for boys are greater than girls. So this is for men, this is for boys, and this is, then you subtract this from this, and then you get the effects of girls, which are not statistically significant. So the figure depicts here the results from the interaction model. So the relative ability of effects on STEM career aspirations is larger and statistically significant only for boys. So before moving on, I just wanted to give you a sense of how large the estimated effect of relative ability is. So I am interpreting 0.083, which is you can get from the third column here, right there. So for boys, and we actually multiply it by a 1 standard deviation in relative ability. So we can get what is the changes associated with a 1 standard deviation in increase in ability rank in terms of here STEM career aspiration. So 1 standard deviation increase in ability rank increases is associated with about 2.4 percentage point, because I'm using linear probability model. So you can easily understand this number, right? So 2.4 percentage point increase in the possibility of aspiring to pursue STEM career. So this is about 16% increase in the STEM career aspiration, given about 15% of boys reported having STEM career aspiration, right? Or maybe more plausibly, more reasonably, we can think about moving a student to different classes. So his ability rank may increase by not, of course, not like a full 100% percentile, but maybe actually 0.1 rather than a full 1 percentile, but 0.1 percentile may be more reasonable change we can consider, right? So this is approximately 9 students up or down. So like moving a student, male student from his class to a different class, he can kind of climb up about by 9 students in the ability ladder. And then that leads to 1.7 percentage point increase in STEM career aspiration, which can be translated into like 11% increase given average dependent variable, average STEM career aspiration 15%. So this is benchmark for your own interpretation. So because of time constraint, I'm going to move on. We're almost done, so don't worry. So our results also provide support for the second hypothesis, gender effects on STEM career aspirations. Gender effects of relative ability on STEM career aspirations. So finally, in this table, we show whether gendered effects of relative ability on STEM career aspiration depend on contextual gender math stereotypes. So we're using a 3-way interaction model here. And as you can see, again, the negative and statistically significant 3-way interaction term implies that differential impact of ability rank on STEM career aspiration for boys and girls. The gap we have seen in the previous slides is conditional on student exposure to class level gender math stereotypes. So for easier interpretation, I plotted the results here. I use a negative 1 standard deviation below mean and 1 standard deviation above mean, and I actually draw this graph. So as you can see on the left-hand side panel, the slope coefficient of boys and girls are exposed to low level of gender math stereotype, right? -1 standard deviation are both positive and nearly parallel, right? But in the right-hand side, for the higher level of gender math stereotype, and the slope coefficient of girls right here is obviously flatter than that of their male counterparts, right? So these contrasting patterns suggest that when exposed to more classmates who believe that boys are better at math than girls, and girls do not benefit from a higher ability rank, right, in developing aspirations in STEM careers, as boys do. So this is a support for the third hypothesis. So you can just read it. So this is what I think actually this paper contributed to the existing literature. And there are some limitation over here. Mainly, it's about the data, the variables and data. So STEM career, the measure to capture the STEM career aspiration is kind of a little bit rough. It's not specific enough to kind of separate different fields in STEM, different disciplines in different disciplines in STEM fields. And there, based on in light of our results, and I actually kind of thought about some directions in reducing gender disparities in STEM fields. Because again, of time constraint, I just leave this slide to you, and just you can think about this. All right, so this is it.
All right, Professor Kim, thanks a lot. This was a fascinating presentation. Now floor is open. So if you have any questions, please let us know. Professor Kim, can you close down the PowerPoint file so that we can see all?
Sure.
Probably we may return to that.
All right, no problem.
Yeah, when the questions are coming in. Yeah, Rebecca, please go on.
Oh yeah, hi. Thanks for the presentation. So I just have a quick question. You're using the students' rank relative to other students in the class. I just want to know, like, how aware are students of their actual rank in the class? Because part of what might be contributing to the gender difference is that boys tend to overestimate where they are in terms of ability, whereas girls tend to underestimate where they are in terms of ability. So it's possible that like the high-ranking boys think they're better than they actually are, and the high-ranking girls think they're lower in status than they actually are.
Yeah, great question. Thank you so much for your question. Yeah, we don't know actually. The most ideal situation in terms of data availability, maybe that we have kind of a question about the students' self-reports about their kind of a relative status in terms of ability, right? So I'm using AdHealth a lot, so National Longitudinal Study of Adolescent to Adult Health. So this is like, you know, a longitudinal data set, not publicly, and very well known, and you know, the adolescent panel data set in the United States, and I'm using it. And in that survey, we have a question about that. So we ask students whether where do you think actually you're standing at in terms of your kind of you know, ability. So they kind of they answer whether they are on average or they're above average and below average. So if we have this kind of information, we might actually run a regression and see whether relative ability is associated with this self-reports of their self-assessment of their ability. But unfortunately, we don't have the data in SEPs. But basically, I don't know. So there are many different ways and different channels through which students kind of evaluate their own standing and compare with different students, but maybe not necessarily through this ability score, because it's a kind of standardized test scores. It's not like, you know, this is not like, you know, the midterm or final exams that are often being publicly open to students, so they kind of check their ranking very you know, regularly. But this is just one-time test, kind of an IQ test or something like that. So I doubt that they have chance to kind of like assess or evaluate their own standing in terms of this cognitive ability. But one possibility is that this cognitive ability should be highly correlated with their academic performance, right? So as far as I know, in China, it's very common that, you know, students kind of put the rankings of students on given exam in the back of the classroom, so that they can kind of see through their the rankings and see whether they are at. So, but I do have a reason why I did not use academic like exam scores, and why actually I prefer cognitive ability score, which is like, IQ score. But basically, this is a channel because, again, the cognitive ability should be highly correlated with academic performance. So I believe, academic performance is kind of a channel through which relative ability might have an impact on STEM career aspirations. But again, yeah, you're correct. So I don't know to what extent they know each other's ability, although they do know their academic performance, right?
Yeah, no, thanks. I just think, given that we know from the literature that there's definitely overestimation of ability on behalf of boys, that the differential utilization and impact of social comparison information, which is somewhat subjective, might also be influenced by the differential assessment of where you fall with respect to other individuals, irrespective of what your objective relative rank is. Just might be something that's worth considering moving forward.
Yeah, sure. Yeah, that is awesome. And I couldn't agree with more with you because so that is kind of is a motivation of this study. So as you said, the boys are more reactive, or they're more sensitive to like social comparison somehow, or they overestimate. And why do you think actually they overestimate? Then maybe the gender math stereotype might work, right? So even if actually they perform worse than girls, but they have been believed, and they have been fueled with the belief that they outperform girls in terms of math ability. But then what really drives this misperception may be kind of a school context, right? So we look at one of many possible social factors or contexts that kind of aggravate or this misperception or stereotypes about math ability. Thank you so much.
All right. Yep. Oh no. Okay. So it was. So Rebecca was satisfied with the discussion. Jean, will you talk or will you write? Jean,
can you hear me? Can you hear me?
Yeah. Please go on.
Okay. So thank you for the presentation. I have a few questions for you. CEPS, CEPS has a few advantages in terms of the data. I was wondering why some of the stuff that you have not looked at. For example, it does have a large number of school characteristics. Even teachers' interaction with students and the academic environment of the schools, school ranking too. School ranking is there too. And I also was wondering, there's a lot of family-based covariates that might be very important, such as parents' expectation for, children's educational achievement. And there's also data about parents' participation in school, like parent-teacher conferences and so on. So there's actually a lot of family-level variables and school-level variables that could perhaps help you unpack a little bit of this story. And we've used this data before, and we've done a lot of the multi-level analysis, looking, as you say, this is a school-based sample. And in fact, some 30 school has completely almost all migrant students. So some of those, I don't know if you have included those or not. You might want to look at the student composition as well in the school. So the bottom line is, I was wondering why you didn't do multi-level analysis and look at the interaction between family and school level factors that actually SEPS has very rich data. Thank you.
All right. So great question. So yeah, you are expert at the SEPs, and I have a very limited experience with the SEPs. So thank you so much for referring me to a different data sources in the SEPs. But first of all, yeah, of course, we could have done a different methodological approach, looking at the effects of a social school context. So as you just mentioned, and random effects or multi-level modeling is an option. But the main idea here in this study, so I actually used quite amount of slides explaining where the idiosyncratic or exogenous variation might come from, right? So as I've shown you in the balancing test results, and school characteristics or classroom characteristics are supposed to be highly correlated with parental characteristics and individual student characteristics, right? So multi-level modeling may actually address part of this like issues using a different approaches. I'm not an expert at random effects model or multi-level model, but actually the assumption here is that, not assumption, we empirically show that school characteristics are highly correlated. So who are attending a more the schools with better performing students, right? So we wanted to kind of take care of this in its entirety, right? So then, but now we're kind of leveraging the class to class variation strategically. So it's a similar approach. So we're using the clustering data, but when we actually use a multi-level data, we want to actually examine the school effect, right? But now I kind of decided to sacrifice, like as you said, it's a rich data set. We know a lot about schools, but I kind of use a fixed effects model, so we get rid of it. So there's no unobserved heterogeneity at school level and school by grade level. But now we're actually then like zooming in and looking at a smaller variation, but is likely to be exogenous, right? Because given school, you're attending the same school, but you're randomly assigned to different classes, and you're randomly given different pure exposure, right? But school, it's not it, right? So schools, which school do you want to go? It's a function of a lot of different factors, right? So you can't really, using the data, you can control for that in any way, right? So that the approach is a little bit different, but the main objective of this study is to identify causal effects of pure context. So I think this is a different approach, but it's more common in economics and also some demography studies. So that is why I did that. But still, there is a possibility that I can kind of take your advice in more practical ways. And I might actually look at some heterogeneity effects, right? So again, actually I did the similar thing using a class level gender math stereotype. We looked at like heterogeneous effects and gendered effects of relative ability on STEM aspiration. But I do believe that there might actually be some school level effects, right? So if you split the sample based on the information that are available, then we might actually see some different patterns that we may be able to elicit, right? So that is highly, it's kind of doable, and I think it's going to enrich our maybe future study. Yeah, that is the main idea. And then about the control variables, yeah, if you really believe, if you are convinced that the variation that I'm using in this study are really at least quasi-random, And adding more controls, I don't think it's gonna do much to help us estimate more efficient or less biased coefficient, I guess. I think actually by adding or controlling for more covariates might squeeze a standard error a little bit more, but I think we do already have a pretty precise estimates, I think. So that is why we just added, added a more parsimonious set of covariates rather than like a dumping in all the possible covariates, because we have a kind of quote unquote firm belief that the variation that we're using are quasi-random.
Thank you. If I could follow up with a small comments, that would be, yeah, just very quickly. I think we can argue about different methodologies and advantages, but I wanted to say that the literature for the gender differences in math ability and STEM career pursuits is that at least in China, the work has been girls has been scoring higher in math until even adolescent age and even until high school. And so and they also do better in school. The reason why then they have lower aspiration for STEM, a lot comes from the expectations of the teacher and the school and the parent. So yes, looking at causality is important, but the story, you can't tell a lot of the story about why this is happening. And expectation abilities certainly is a big part of the story that should be told. Thank you.
Appreciate it.
Regarding the effect of school ranking, Jean just brought up, I thought that your S term, the fixed effect term in your study, I thought that it controls for that, doesn't it?
Sorry, can you say that again?
So Jean just mentioned about the school ranking effect, which means that there could be some effects of the attending the elite schools, elite secondary school or whatever, right?
E-school, yeah.
Yeah, so yeah, there should be some of those kind of schools in your sample probably. And I thought that the effect of the school ranking was controlled by having the fixed effect term of S. Wasn't it the case? I thought that, yeah, please go ahead.
Yeah, I mean, basically, I control for school by grade fixed effects, which means we don't really care about which school students attend, because all the possible unobserved heterogeneity at school level and at the same time in the grade level have been removed, right? So, but if you're interested in looking at whether there is a kind of school effect, and you could have kind of split the sample based on the school characteristics and see what are the different patterns between these two different school. So I mean that is kind of pretty doable, but in my own so this basically the estimate that I estimated are like average treatment effects, right? So there can be different sources of heterogeneity effects. So one of them is again as the professor Jin Yang and also Jinho Son just mentioned, and I do believe they're like very important school effects, right? But again, it's another challenge that you have to face is that school effects is causal effects. So again, multi-level model is is a valuable approach, and I do have full respect, for the approach as a methodology. But I think it's because causal inference is beyond like a methodology, right? It's more conceptual, and at the same time, it's kind of we have to actually see this causal inference as a spectrum, right? How causal it is. But in terms of this spectrum, I don't think multi-level do much, too closer to a causal causality. I think, might have a different view. But if you have your own justification, how actually this school effects that you estimated from multi-level modeling is really causal, and I can buy it. But most of cases, school effects are kind of combination. It's sometimes are not really causal, but it's somewhat hard to interpret as a causal. So I mean, but in this study, basically the main motivation was to identify causal effect. That's why we, again, at a very high expense of more interesting stories, unfortunately, as Jinho just said.
All right, we can have diverging viewpoints about the methodology, so that's fine. Peter, do you have a question?
Yeah, I got a short question. Thanks for the presentation. And I, in the multivariable regression model, what's the association between absolute ability and STEM aspiration? So it's shown in the table, but the coefficient was not seen, because as Prof. Young mentioned, that what I expected to observe before proceeding to method section of the presentation was some multi-level model that investigate the cross-level interaction between individual ability and school-level ability, so that we can see whether individual absolute ability matters for STEM aspiration in different, school that has a different level of students in this case. So I just wonder, is there any significant association between absolute ability and STEM aspiration? Thanks.
Yeah, great question. Thank you so much for the question. And I think actually in educational literature, the common practice is to examine big fish little pond effect, is to use individuals' absolute ability or test scores, and using average test scores for a reference group, and you use like the interaction term, right? Yeah, I mean, so in that sense, then I think actually, okay, ability rank, the absolute ability, of course, is supposed to be correlated with STEM career aspirations in my data too. But the main, different, strategy to tackle the same important issue, right? So if you use multi-level model, that is a more common practice. But the problem here again, the peer level, characteristic here, the peers' test scores, are they really exogenous? There are no chance that you select into certain peer group or certain classroom or certain schools. So it's really hard to sell this kind of assumption, because as I just shown you in the slide, and there are large array of variables that are correlated with classroom mean ability, right? So that, what does that mean? That means students select into specific peer context. So through different mechanisms, but one of the main mechanism is parental school choice, right? So where you live, and then whether you are better performing or not. So I mean, it's a combination of different factors. So it's hard to disentangle or control for all these selection factors. So if you can convince people that the pure context is really exogenous, and then from then on, I think it's pretty hard to interpret the interaction term, the coefficient of interaction term. So that is why you ask a good question, whether the absolute cognitive ability is associated with STEM career aspiration. Yes, it is associated with STEM career aspiration. But once we actually we added the relative ability measure, and then the statistically significant coefficient of absolute ability are gone. So that means even if, so the reason why actually we did not include the coefficient of cognitive ability, absolute cognitive ability in this table is because we're not very much of interested in interpreting the coefficient, even if it is statistically significant, because the only reason that we include a control for absolute ability is to really isolate, or we wanted to kind of zoom in to compare two different students at the same level of cognitive ability, but exposed to the different peer context because of random assignment, and then their rank differs, right? Even if they have the same cognitive ability, because of this, different ability distribution of peer groups, their rank different, right? So I wanted to really look at that, the particular group of students. So that is why we control for absolute cognitive ability. So we did not intentionally did not interpret, because then we don't really know what that coefficient really means and the magnitude of it. How can we really interpret it in a meaningful way?
All right, Agnes actually left a question in the chat room. Professor Kim, would you look at that and answer?
All right, so I'm wondering, do we need to add a family level fixed effects to control for some parenting characteristics? Though you mentioned family level characteristics may highly correlate with the school level fixed effects. Family level fixed effects. So, okay, so it's a great idea. This is wonderful, question, I think, because I am a big fan of sibling family fixed effects. So basically, but the problem, again, the data problem here. So in SAPS, we don't have family identification. So if the question is about family fixed effects, is that right? Is that family level? So yeah, family level fixed effects. So to implement family level fixed effects, we should have a siblings in the same data, but we do not have a family ID. So it's impossible that we kind of control for family fixed effects. But again, so there's a different source of confounding, right? So if we do not leverage like a class to class, quasi exogenous variation, then that is a big part of the story, right? We have to actually think about how to deal with this, family level confounding, right? Because again, students are going to different schools because of a parental character, based on the parental characteristics, right? But then another assumption that we have to have, maybe not really necessarily, if actually two children go to the same school but different grades, we definitely can adopt a family fixed effects model. But if actually they are in the same school, yeah, if they're not twin, yeah, they are supposed to be in different grades. So I think actually it's no problem, right? So yeah, that's pretty doable. But again, we don't have data. But family level confoundings are one of the most important confoundings. If we may, for example, if we use a multi-level modeling and how to control for these determinants, family level determinants, should be very important technical or empirical challenges to tackle, I guess.
If I could just say, with the school-based sample, it's very unlikely to have the sibling samples that you can use. Also, in the context of one-child policy in China, that's almost impossible.
Exactly. Yeah. Of course. But EdHealth, it has like it's a school level. School-based survey, but at the same time, it provides family ID. So I use it very much. And
sure,
yeah,
you can use the PSID too.
Yeah, thank you.
Oh yeah, Hushu?
Yeah, thank you.
Yeah, go ahead.
So my question is kind of related to the first question raised during the Q&A session. I'm wondering, I find the moderating effect of class level gender stereotype very striking. the interaction, three-way interaction graph you have shown. And I'm wondering what could be the source for the class level gender stereotype. And I remember a couple of years ago, there's a paper using the same data working on SEPs, using the same data to look at the effect of the gender of the mathematics teacher in the class and see how this might affect the students' mathematics performance and their own belief in whether boys are better at mathematics. So I wonder if you have checked whether the class level gender stereotype is kind of due to the gender of the mathematics teacher. So if they have a female mathematics teacher, then maybe the students in the class will have weaker belief that boys are naturally better at mathematics. Just a question on this.
Yeah, this is an awesome question, and I like your comment here. So what is the source of class level gender stereotypes? So I have actually two different answers to your question. So first, more data related issue here. Methodological point of view, and another one is more substantive. But let me just try this. So basically, again, as you said, there should be a larger variation. I can just expect that there are larger differences between school variations than within school variation in terms of class level, gender stereotype. So which school you go to, it may actually be more important to what extent you're exposed to different levels of gender stereotype. That is my expectation, because within school, in two different classes, and if actually there are class level variation that we can identify, we actually use the class level variation actually, because there is a variation. It's not exactly same. Even if you kind of randomly assign students to different classes, there can be some class level differences in terms of gender stereotype, right? So we're using relatively smaller variation in gender stereotype at class level, right? So it's not like comparing highly prestigious school and very low performing school. And I don't know, I mean, you have your own answer to this question, which school is more has a higher levels of gender stereotype at school level, right? But anyway, so there should be actually larger differences, but within same school and different classes, the variation should be very small. Then the variation, that is why I believe is generated by random chance, highly likely. But if it's, over the semester, it might intensify because of, again, you just mentioned about the possibility that teacher, right? The gender of teacher or the peer characteristics, that might actually, a source of a higher class level gender stereotype. Yeah, of course. But one thing that I can tell you, whether you did not ask this question, but if you really think there actually might be some, confounding or class level gender heterogeneity may not be generated solely by chance, and there are some, teacher effects there or other effects, in there. That's a highly probable, story. And actually, that is why we run, some simulation, and we run some statistical test whether there is a correlation between teachers' information, for example, teachers' gender and teachers' years of education and teachers. I forgot another variable, but we actually use 3 different variables, see whether there's a correlation between class level, student composition measure, and the teacher's characteristics. And we found nothing. So that means even if it's highly likely that teachers play a crucial role in affecting the class level atmosphere, especially with respect to gender stereotype. But at least in our data, because our data is like a cross-sectional data, although staff says like, I think there are like 3 waves, 2 waves, for sure 2 waves there, but I don't know if actually 3rd waves are available. But we're using a cross-sectional data. So I can really say that the possibility anyway, so this is like a methodological answer to your question. So that is what I think about your question. So at least there are no correlation between teachers' characteristics and class composition given in the same school. So, but again, it's a very important issue and question to ask where this gender stereotype might have come from, right? So this is another very important research question that I am also interested in personally.
Okay, if the participants are not, okay, if you don't mind, then I may have some questions. So Professor Kim, would you go to the slide number 33?
Just hold a second.
Yeah, take your time.
Yep.
What I wanted to look at was the effect of gender, female. What happens if you employ female variable in model number 1?
So here?
Yeah.
Without controls?
With or the same conditions.
So in this case, the first column shows the bivariate results. So you mean like
I see. You want bivariate, not or just correlation?
No controls at all. No.
Oh, I see. All right. So what I wanted to find out was whether the effect of female significantly decreases when you controlled for the variables you were interested in, like a mobility with rank and the correlation. The interaction between the rank and female and other kind of things. But what I see from this table, I'm not sure whether it's consistently correlation, but what I see from this table is that the effect of female actually does not very much decrease after accounting for all the measures you were interested in. What I'm trying to say is that I wanted to see the relationship between the nature and nurture hypothesis. So you actually brought in all the nurture part coefficient you could. And then what I see here is that if I interpret it correctly, the gender effect does not go away nor decrease. So what does that mean? Then your model of nurture, did it actually explain the effect of nature or being female away to some extent? How would you answer to this question?
I think actually, I don't know if actually, understand your question correctly, but let me try. So basically the nature nurture, divide or explanation is about, when it comes to kind of math ability, not like STEM career aspiration. Of course, math ability, should have some correlation with STEM career aspirations. But in this case, I think actually you're trying to say like, there should be, so nature explanation is already, I think, nullified, right? So that means there are no gender differences in math ability. So that is why I think that is explanation, like, maybe 5-10 years ago, there are like people who
No. With regard to the STEM career aspirations.
Yeah. So nature explanation, if actually nature explanation should work, and we should see the gender differences in cognitive ability, right? But we did not see any of evidence on that. So that is actually why actually I discussed, on nature explanation in the very first, the beginning of the presentation. But here, then everything is about like nurture explanation. So so that is why I think I don't really see how we can get some idea about nature explanation here. So yeah, I don't know, sorry for that. I don't think actually I misunderstand your question, but
okay. So my point was that if being female is, how can I say, naturally related to the lower expectation or lower aspirations for the STEM career, what I expected to see was a kind of significant reduction in the variable of female, but it seems that I don't see that. So that was my concern. And second thing, this might be a trivial thing. The R squared, it's somewhat small. I mean, it started from 0.004 and it increases to 0.061. Why is this the case? I mean, is it really hard to explain the career aspirations in this way?
I don't believe R square is, I mean, R square is important because it's variance explained,
Right,
actually, yeah. But in most of social science research, I don't think, people, are very keen on, R square. But basically here, moving from model 1 to model 2, as you can see, there are like huge increase in percent because we added like ability measure, right? So that explains quite amount of STEM career aspirations. But at the same time, again, the variation, the outcome, the dependent variable is binary, right? So then in this case, I don't think actually R square is very, that informative, I think. And where I'm feeding a linear probability model. So in this specific model, and we're using a binary variable and R square. I don't think I don't think actually we use the same way to explain, interpret the R square in the same way that you're using OLS with continuous measure with more variation. So, but basically, I don't know. So if you have a better explanation on that, I really want to figure that out. But yeah, but that is my answer. And I kind of get your answer, the earlier question. So I think in this case, so we are trying to, what we found out was like there is a huge difference in STEM career aspiration by gender, right? So women, even if given that I've already shown you that there are no gender similarities in cognitive ability, and like we do have another set of evidence that the girls have a parity with boys in many test scores, right? But then we see this huge STEM career aspiration differences. So as far as I remember, 15% of boys reported having STEM career aspiration. By contrast, only 3% or 4% reported 4% of women, girls, having a STEM career aspiration. So this this coefficient, so negative 0.131, that really reflects the differences, right? So then what we actually did in this empirical model is to explain where does this difference come from, right? So the possibility is relative ability, right? That is why actually we use the interaction term. So see what's going on here. If we actually look at there is a gender differences, I mean statistically significant interaction, then like we kind of provide some evidence of the importance of a relative ability as a kind of part of a source for the gender differences in STEM career aspirations.
All
right? So basically the answer that I just gave you is kind of well reflected in this table, right? So as your relative ability increases and females, STEM career aspiration does not react to their higher relative ability, but boys' relative ability has something to do with STEM career aspiration. That's a kind of a story that we wanted to emphasize as a source of gender differences in STEM career aspirations.
All right.
So,
yeah. So your aspirations variable, the outcome measure was a yes or no question. In other words, it was dichotomous.
Binary, dichotomous.
I see. All right. Can you unshare the PowerPoint slide so that we can all see? We can see all the persons?
Sure, no problem.
All right. Thank you. Any other questions? No? All right. Thanks for your time. And Professor Kim, once again, thanks a lot for joining us and giving this wonderful talk.
Thank you so much.
Thank you.